Hi, my name is Reagan Shield, and my partners are Will and Min. And today we will be discussing the general methods for generating random variables. This is presentation number 4 for Engineering 460. Just to go over the contents of this presentation, we will have Chapter 3. 3.1 contains inversion of the CDF, and 3.2 contains the envelope reaction.
So hi, I'm Ming, and today I'm gonna talk about inversion of the CDF for random number generator. So the inversion of CDF is used for its generality and simplicity. And the definition of the CDF of the random variable x is just the for the probability of the random variable that is the smaller or equal to x for all x. And if f is a monotonic increasing, then we would have this one, which is the probability of f of x is less than r, and so this will give us the result of the probability of the random variable less than x equal the probability of the random probability of the f of x is less than r and 0. So our example using the inversion of CDF to generate random variable is this. So the fx is the distributions, and the CDF of fx is this one right here, and we're gonna note s equal to r, and so the random variable is basically created by inversion of r in the last line here, and that's it for the inversion of the CDF to generate random variables.
Okay, so I will now be going over section 3.2, which is envelope rejection, and this is another method to generate random variates. So envelope rejection is basically a method to sample variates using repeated rejection until a generated variate is accepted. So as you can see highlighted in blue, we have our density function, and this is simply f of x equals h of x over the integral from negative infinity to infinity of h of x dx. And this function is what we'd like to generate our variates from. However, the inverse of this function does not contain a closed form solution. Therefore, we must come up with a new density function or proposal. So here's our proposal function. It is g of y over the integral from y on, included in support of g of y dy, and variates are easily generated from this new density function, which we will show on the graph in just a second. Now that we have a new proposal function, we can generate a proposed variate. The variate, let's say y, is either accepted with a probability of h of y over g of y, or it's rejected. And if this variate is rejected, then the process is repeated until one of the proposed variates is accepted. So here we can see envelope rejection on a chart. So we have our g of x and our h of x. And as you can see, both of the functions will intersect one another in various places. So the goal is to use rejection so that all of the accepted variates will accurately represent the distribution f. Now note if our two functions are equivalent at a single point or multiple points, and as we can see they are in this area right here, then g envelopes h. So here we have an example where you can see our proposal, and here's our target. The target we don't really have any information on. This would be, if you remember, our h of x, which is our original density function, and then we have our g of y, of course. So here we would have our h of x, and then here would be our g of y. So our proposal function we do have information on, and it's very easy to generate variates from this curve. However, this curve down here is a lot more complex, so we have a harder time generating variates from that one. So that's why we have our proposal function. And as we can see, our accept and reject, and this just shows that rejection until you get an accepted variate. Here's our reference. It is our textbook for this course. Thanks for listening.